Hello, welcome to part 2 of Introduction to ggplot2. We're going to be diving a bit more into the grammar of graphics in this video. So the grammar of graphics is the logic that guides the ggplot2 package. You can think of it as a way to layer graphics and build a plot up with layers. It's based on a system that Leland Wilkinson developed for graphics. There's a book you can read if you're super interested, but you don't need to read the book to understand how it works in ggplot2. So our objective here is to understand the additional components of a ggplot, aside from the just 3 main ones that we covered in the last video, and how to use those components to build more complex plots. Okay, you guys are going to hear my kids like really yelling in the background of this video. I don't know what game they're playing, but it's loud and it sounds fun. Okay, so let's go through where we left off in the last video. We went through the 3 components of a ggplot object that you absolutely need in order to build a basic plot. These are the data, aesthetic mappings associated with that data, and then at least one layer. A layer is usually created with a geom function. So what we're going to do today is take a deeper dive into the layers specifically. So the components of the layers are the geometry itself, a statistical transformation, a position adjustment, and 1 or more scales mapped to aesthetics. And just a note here, I didn't mention it in the first video, but now you should know that those 2 essential components, the data and aesthetic mappings, their appearance is controlled by scales, this thing that is a component of the layer. So we'll talk through what that means. All right, so a layer, as we've said before, it can be a point layer, a line layer, polygons. It's just how you build your plot up to look the way that you want it to look. Typically, this is done with a geometry call. In the code example below, we're adding a point layer below the main ggplot call. And every layer needs to have these following components in order to get it to display correctly. So it has a geometry. Geometries control basically the type of plot that you create, whether it's a bar plot or a scatter plot. The geom is often named for the type of plot that you're creating. So some examples are at the bottom of this slide here. Geometries often have an accompanying underlying statistical transformation. So for example, for geom box plot, the statistical transformation is box plot. And by statistical transformation, we mean the way that ggplot2 is transforming your data under the hood in order to get it to display the way that you've asked it to. So for a box plot, it is actually performing a statistical summary on the variables that you're adding to the plot in order to display them as a box plot with a median and an upper quartile and a lower quartile, etc. So a statistical transformation is often just an identity transformation where nothing actually happens to your data. It's just displayed as is, but there are some geometries that are associated with particular statistical transformations like geom box plot or geom histogram, where you're binning your data, and that's for statistical transformation. But most of the time, if you don't notice something explicitly, your statistical transformation is probably just the identity transformation. Next, every layer has a position adjustment. This is how you control the position of the elements within a layer. So for example, whether you want a stacked bar chart or a dodged bar chart to make a group bar chart. So those position adjustments are how you do that. The default for a bar, I think, is stacked. If you wanted the bars to show up next to each other, you would have to add this position adjustment to dodge the bars. So the position adjustment, just like the statistical transformation, is often a default or it goes unstated. Usually you won't notice the position adjustment until you need to change something about the appearance of the elements within a layer. The last component of a ggplot2 layer that we're going to talk about is scales. The scales, as I denoted in that little bracket in the earlier slide, the scales are what control the appearance of the mapping from the data to aesthetics. And what I mean by that is every aesthetic in your plot, so every visual component of your plot, like the x-axis, the y-axis, the colors, every single one of those aesthetics has exactly one scale associated with it. So for example, the x-axis, if you're plotting continuous or numeric data on your x-axis, that the scale associated with that aesthetic is a continuous numeric scale. If you're plotting a discrete variable on the x-axis, like a category, then that x-axis aesthetic is associated with a discrete scale. So every time you map something from your data to an aesthetic on your plot, it gets assigned a scale, and that scale is how you control the appearance of that variable on your plot. So whenever you want to change the appearance of stuff on axes or guides or legends of your plots, you will probably be doing so via the scale. There are a few different types of scales. We're just going to cover the most common ones. Position scales are used for numeric or continuous date-time data. Color scales are used to map your data to different color scales, and there are a bunch of different options there. Manual scales are used to map discrete variables to custom aesthetics, and that could include custom discrete color scales. Scales, I think, are one of those things that makes more sense when you're working with them in R rather than talking about them. So the last thing that I'm going to mention before we head over to R is faceting. And facets are not a component of a layer. Faceting is what lets you create multiple small plots by subgroup. It's sort of unique to ggplot2. And it's like subsetting your data down to separate groups and then making a plot for each group and then lining up those plots next to each other. It can be really useful in a variety of different situations. And the way that you add faceting is with these calls to facet wrap or facet grid. So altogether then, a full ggplot specification might look like this for a single plot. In the top layer, we have the ggplot call that sets some aesthetics that get inherited by the rest of the layers. We add some layers like a geom point layer and a geom smooth layer. And then we might adjust the scales of the aesthetics that we specified within individual layers by adding our own manual color scale to map some discrete colors of our choosing to the variable prevalence. And then at the end, you might add a faceting specification to create individual plots for each year. All right, we're going to head over to R. This is the website for the course GitHub repository where you can find the script that we're about to go through in R. Okay, here is our part 2 script for Intro to ggplot2. We'll load up the ggplot2 package. We'll be using the same cod parasite data that we used in the first video. And just as a recap, the components of a ggplot, so a plot object, is we have the default dataset and the mappings from variables to aesthetics, then one or more layers, and also you have a coordinate system. The default is Cartesian, so we didn't go over it in the lecture. There are a few other coordinate systems you can look up as well, and a faceting specification if you want. And then the components of a layer are a geom, a stat, a position adjustment, and scales. So the goal here is to get a bit more familiar with those components within the layers to understand scales and statistical transformations a bit better, and just to get a sense of some common types of plots and how to make them, and do a bit more advanced plotting than we did in the first video. So our first plot is going to be a box plot. So we're going to set this so that all of the other layers inherit these aesthetic mappings, where year is mapped as a factor onto the x-axis, and weight is mapped onto the y-axis aesthetic. And let's see what this code gives us. So you'll see some warning messages about removal of rows containing non-finite values or missing values. All that's saying is that when it tried to do the statistical transformation, it ran into some issues with missing values or non-finite values in your data, so those values were omitted, and you should probably check out which ones those are on your own whenever you get warnings like that. Okay, so let's talk about this plot that we just made. So our data is the cod parasite data, our x-axis is year, and we wrapped year in factors so that we would actually get a discrete scale onto the x-axis. If we hadn't wrapped year in factor, year is numeric, and so it would have defaulted to a continuous scale. And it would try to plot all of these intermediate values because it sets some default spacing on that continuous scale. And obviously when this is year data, this isn't what we want. So we wanted to treat them as discrete variables, and that's why we wrap them in factor. So by doing that, we've automatically gotten a statistical calculation by group. So that's why we get these 3 box plots here. In the next layer, we added some points and we jittered them on the x-axis, since it doesn't matter where in that category they appear on the x-axis, as long as they're all grouped by the right year. And we mapped the depth variable to the color aesthetic. So since depth, again, is a numeric variable, show that here. Depth is a numeric variable, so it automatically got assigned a continuous color scale because depth is a continuous variable. If we had wanted it to be discrete, we could have wrapped this in another factor, but that would result in the generation of so many levels in the factor that the colors would quickly lose their meaning. So we're leaving it as a continuous scale here. So by mapping depth to the color aesthetic, a scale, a continuous scale, was automatically generated for us. And that's what we see over here on the guide, is that, that guide or legend for that continuous color scale. And this layer that we've added right here is the geom-boxplot layer. We are controlling the transparency of the boxes with this fixed alpha aesthetic. And I've added this outlier.shape equals NA to get rid of the outlier dots that get automatically plotted with the box plot. I'll show you what it looks like when you include them. So you can see that they are plotted right up here as the outliers, but those outliers already exist as jittered data points, so we don't need to show them again in the box plot layer. So I'm telling it to map to a shape that is not applicable, and that makes them disappear. So that's a basic box plot. Let's make a scatter plot, and we'll add a faceting specification to this plot. So as I go along, I'm going to start omitting some of these explicit argument names because the more plots you make, the more shortcuts that you'll take with your typing. The ggplot2 defaults are really good, and so you can save yourself a lot of typing by using them. So in this scatter plot, we have put length on the x-axis and weight on the y-axis. We've added a point layer, so we're plotting those observations as points, and then we have wrapped our years into different facets. So the facet specification does a lot of the work for you. It creates your 3 individual plots, and unless you tell it to do otherwise, all of the scales on the x and y axes will have the same limits. If you want to let those limits vary by facet, then you can do scales equal free, and that will set defaults according to the data points observed in each facet. If you want just the x-axis to be free, you can do free x. If you want just the y-axis to be free, you can do free y. So that's an example of faceting. There's an exercise to do on your own here to try to explore that a bit more. Next, we will make some bar plots. So you'll be using the geom_bar function, and the default statistical transformation for the geom_bar function is count. And so what that's doing is it's looking at your data and it's tallying them or counting them up by the variables that you specified, in this case year, and that means that it's not going to accept a y aesthetic if you try to give it one, because it's going to plot the count onto the y-axis automatically. So let's run this. So what this is doing is counting up the number of observations by year. And I've done a couple of extra things here that we'll talk about. For a geom-bar, to specify the colors of a bar plot, you use the fill aesthetic. So we've mapped the year variable, the year variable to the fill aesthetic here. And I've also told it not to show the legend for this layer. If you change this to true, then it will generate a legend for the color scale or the fill scale that you specified here. But with a bar plot, it's pretty obvious which color goes to which variable, so I set it to false. And then the next thing that I did is I gave it additional modifications to the fill color scale. I told it which color palette I wanted to use. Scale fill brewer is a function that is built into ggplot2. It's what allows you to set colors using the color brewer package, and you can look up the documentation to that on your own. If we hadn't used this, it would have defaulted to ggplot2's default colors, which I love because I love ggplot2, and so at this point the colors make me nostalgic. But usually you're going to want to use a different color scale. Scale, fill, brewer, and all of the brewer functions built into ggplot2 are just one way to achieve that. You can also set them manually, or we could have set them manually with scale, fill, manual. And if you are providing a discrete manual scale, then you have to provide the values. One value for each unique level in the variable that you're trying to give a color scale. So since there are 3 years, we need to provide it 3 colors. So we can do Dodger blue, purple, and yellow 4. Let's see what that looks like. Not much better, but you see what I mean. Okay, let's move on to the next kind of plot. And this is just going to be another bar plot, but the goal with this one is to show us the difference between the stat of count versus a stat of identity versus a different kind of stat. So, and position adjustment. Okay, so for this first plot, let's see what this gets us with depth on the y-axis, year still on the x-axis, and this time we're going to make a bar plot with the different stages as the fill and a stat of identity. All right, so what this shows you is that the default position adjustment for a bar plot is stack. So by default, it will stack your groups on top of each other, which is sometimes useful, especially if you have like proportional data that adds up to 1 or 100, but not so useful here because it gives a distorted view of the depth scale. So if we did a summary of the actual depth column in COD data, we see that the maximum depth is actually less than 300. So this y-axis scale doesn't make a whole lot of sense until you realize that it has stacked all of the observations on top of each other and it's just summing them up. So if we change that to have a position of dodge, we start to get something a little better. And now we're seeing the actual depth values that make sense, but we still don't know how many observations that each bar here represents. So this still isn't the most useful plot, but I just wanted to show you the difference between the position adjustments of stack and dodge. So we're still going to keep the fill as stage. We're going to add a statistical transformation of summary, and specifically the function that we want to use, which we add with this fun argument is, let's say we want to know the median depth for each stage in each year. So, and then we still need to add, let's see, I can't remember if we're going to need to add the position adjustment here. I think we do because it's going to stack them at first. Yeah, so again, we're back to that default position adjustment of stack. Let's do a position of dodge. And that should give us a slightly more useful plot here. Okay, so I'm just going to clean up the script a little bit. So this is going to be with a statistical transformation of summary, position stack, and then the one right below it is the same one, but instead with the position of dodge. And then there's an exercise to do on your own here. And finally, I did want to show a plot with date info on one of the axes. So what we're going to do is use the built-in dataset faithful, and you can look that up on your own if you're interested in where that dataset came from. Just do $faithful to bring up the documentation. It's geyser data. And what we're going to do is add a column for date because the faithful data doesn't have a date column built in. It's just two columns on their own, eruptions and weighting. So to add a date column, I'm just using the sequence.date function to add a column with date info that we can then map to an axis. So now we should have a third column here in our dataset D. So we have this date column, and let's put that date column on the x-axis of a scatter plot. And what we're doing, instead of showing the plot right away, we're saving it to this object P, and that allows us to build up layer by layer. So here's the scatter plot that we just saved to the object P. And now we see we have date on the x-axis. So ggplot recognized that column as a continuous date info, and it mapped it to the x-axis with its own scale, and that date scale has default breaks. It looks like about every 4 months. So let's say that's not the scale that we wanted. We wanted to add different breaks along the x-axis by date. So we can do that by adjusting the scale that is associated with the x-axis. It's called scale x date is the function. If you had time info, it would be scale x date time. And we're going to specify that we want the breaks to happen every 2 months along the x-axis. So now we have our breaks happening every 2 months instead of every 4 months. And you can see that the labels have changed. The default labels have switched to an ISO date format with year, month, and day. And let's say we liked the month labels, so we want to keep those. So to adjust that, you can use this date labels. So if you want to find out what those are, you can look up the strip time function. So all of the different conversion specifications are listed here. And if we use this lowercase b, that's going to put the abbreviated month name in the current locale. And that what those show up as is going to be based on what your own computer system recognizes as your locale. So in my case, it's going to show up with the month abbreviations in English. So we see these on the bottom, and our labels are a little bit closer to what we want them to be. So that's just an example of a plot with date on the x-axis. So that's it for this video. This script is uploaded to the course repository, so you can download it and follow along with it on your own and do those exercises as you go. Thanks for watching, and I hope this was helpful.